Good afternoon. I'm Scott Van Brammer from Widener University near Philadelphia, and I'm going to talk today about the experience I had using the LC optimization tool from ACD software during the pandemic to save the day for my instrumental analysis class. And so the course I used this with was an instrumental analysis class that I teach to junior chemistry majors every year. The experiment that we were getting ready to do was a sort of traditional HPLC experiment where I have the students bring in caffeinated beverages and we find out how much caffeine is in their coffee or their Monster or their tea or whatever their caffeine delivery system of choice is. And normally the way I structure this lab, and one of the things I really like about it, is I use this as an opportunity to focus on experimental optimization. And so what I do is I have the students do some research in the literature to find some methods for HPLC analysis of caffeine, and look and figure out what solvents and mobile phase mixtures we might need to use, pick a column, and identify a flow rate. And then we go into lab and we spend 1 3-hour lab period usually trying to optimize the experimental conditions, changing the flow rate and the mobile phase mixture. And then we come back again the next week where they bring all of their different samples in, and we do a calibration curve and measure the caffeine in their coffee and stuff. So that's kind of the setup for the experiment that we're doing. We were in lab on March 11th. Lab started at 2 o'clock. We were in a computer lab and all the students were looking up journal articles, and we were sort of brainstorming and talking about what conditions and settings they needed to be aware of and pay attention to, and sort of figure out what we should start with. When at 2:30, one of the students noticed that they got an email from the university that the university was going to shut the campus down. This was under a state order from the governor, and that everybody essentially had a day or two to pack up their rooms and get out of town. At that time, the university switched to online learning, and that's when I started to panic. The faculty were given about a week to try and come up with a plan and figure out how to completely restructure their courses. I was really scratching my head and struggling with trying to figure out how I was going to teach instrumental analysis under those conditions. But I remembered that I had used ChemSketch years before, and that I had noticed that ACDLabs had an LC simulator component. And so on March 24th, I contacted ACDLabs, and by March 30th, thanks to Michael, I was up and running with a license that I could use for my class to use the LC simulator. And what I'm going to talk about today is sort of what I used in the simulator to teach my students experimental optimization, and talk a little bit about how that all worked out. And so the way I decided to run this was to use Zoom, and that I would share my screen and I would show them the results from the simulator, kind of like I'm going to do with you now today. I had them come in small groups instead of doing this as a whole class, so the students would be able to ask me questions and come up with ideas for things that we could change and modify, and then see what that would do with their results. And so it worked really well. I was able to demonstrate and discuss important LC optimization parameters and experimental design choices that the students would have to make. And from there, what I want to do is go through some of the major things we looked at. So I showed them sort of how to optimize an isocratic system, then use that as a basis then to introduce the idea of using a gradient elution, and then how to optimize the gradient. And then finally, we talked a little bit about column optimization, and that was where we were able to do some things that normally I'd never be able to do in the classroom. So what I want to do next is to share the software screen with you. And so what we've got here is what the screen looks like. And so down here at the bottom is the simulated chromatogram. And so this is for a simple 2-component mixture. And I started off with this just to keep things sort of simple and straightforward. And so this would be sorbic and benzoic acid with a system that's only got 3% of the organic mobile phase. And again, this is an isocratic run. And this is showing the 2 peaks coming out at about 45, 50 minutes. And so you're looking at almost an hour-long run. We do have good, there's nice resolution, so that's good. But we would talk then about how many experiments the students were planning to do. And if there's 10 students in the class and they each want to do a couple of samples and we need to run some standards, it quickly becomes apparent to the students that 1-hour run times mean that either they're going to have to come in for lab for from 8 o'clock in the morning until 10 o'clock at night, or that we're going to have to really scale things down. And so this is where it becomes really clear how important experimental optimization is. And so the first thing we could do is say, all right, well, maybe if we bump up the organic component of the mobile phase to 30%, maybe then the experiment will run faster. And so during lab, normally we would have run that first experiment. We would have waited an hour to make sure everything was through the column. Then we would have sat around and we'd had a conversation about what to change. And then somebody would suggest, well, let's increase the organic component to the mobile phase. And so we'd set up when we'd run that again. And so here, we would just be sort of looking in the dark. And so maybe somebody guessed 30%. And what we see here from the simulated chromatogram is that we got really fast retention times now, but we've got no resolution and no separation. And what I want to do next, though, is to talk a little bit about some of the other information that's here, right? So here's where you can define the solvent system. Here is where it's calculating the minimum resolution from the experiment, the runtime that's necessary, and K prime. And what this is showing is that we've got no resolution. And then the flow rate, and a lot of these ideas. And then here are some details about the column that can also be adjusted. Over in this window is the listing of the components, the retention time, K prime, the simulated peak width. And so this is based on the column parameters, and then the mathematical equation that was used to calculate the retention time and the peak width. All right, so if 3% is too long and 30% is too fast, students might guess 10% next. And so here we've got a run, and you'll notice that now the background's not all red hatched. And so this markings here are showing the retention time, the dead volume for the column, or over on the other end if the runtime goes too long. And so we're in the sweet spot. So we've got an experiment that's going to take about 20 minutes. We don't quite have sufficient resolution to completely get baseline resolution between these 2 peaks. And so then somebody might say, okay, well, let's try a different value. So you try it to 7.5. And so now we've got good, we've got a resolution. It's calculated here in the software at 1.4, but you can see the peaks are almost baseline resolved. It was really nice with the students to be able to use this to give them a visual to see what resolution looks like and to talk about separation. And being able to see this was much more effective than sort of the abstract conversations that we'd had in class when we were talking about chromatography theory and plate heights and things like that. All right, so what I want to show you next is that there's another option here that we can display what's called a resolution map. And so here you actually can select the organic phase composition, and you can move this with your mouse to adjust the organic phase composition, and it will calculate the simulated chromatogram. And so you see here, as we increase, by the time we get to 20%, the complete peaks are completely overlapped. But what we can do then is we can decide what resolution is necessary and look at the trade-off that you get better and better resolution, but the runtime gets longer and longer. And so that lets you ask the question, sort of, what's most important to you? And then as a class, we could talk about so that we could, we could get this system resolved, right? We could get a well-resolved experiment in 30 minutes. And so we could ask the question, whether or not that's a fast enough runtime that we can successfully complete the experiment in a reasonable amount of time. We're probably still not there. And so then we can start to ask other questions. And so here we can go in and say, well, what happens if we increase the flow rate? All right. So if we increase the flow rate to 1.5 mils per minute, you can see the retention time. It's obviously much shorter. And we still got good resolution. And then, okay, well, so if 1.5 works, well, what if we go up to 2? And as we do this, right, we can again see, right, what are the trade-offs involved. The software doesn't calculate column pressure, and so it's hard to figure out sort of what's the maximum flow rate that you could go to, but that's a conversation you could have. There's some other programs that'll let you, for a packing material, particle size, solvent, and flow rate, what the pressure would be required. And so this gave the students I thought, a really solid introduction to some of the trade-offs involved in experimental design. Now, one of the other things that we can do, remember, at a flow rate of 1 mil per minute, it was going to take about 30 minutes to do the experiment. So one question you could ask is, with the software, can't really practically do this in person, but what would happen if we used a shorter column? What would happen if we got a 5-centimeter column? All right. So now the retention time is a lot shorter. The runtime is shorter, but we don't quite have enough resolution, right? You can ask the question, well, can we offset that by changing the mobile phase to get good enough resolution and still end up with a shorter experimental runtime? And so the software lets you sort of play around with those parameters and see what's happening. But the software also gives you an opportunity to change the packing material size. And so if the particle size is 5 microns, right, in lab, I could never do this. I could never put another column in, spend an hour waiting for the whole system to re-equilibrate and then running some experiments. But with the software, it's easy to say, well, what if I change to a different column? And I can have the students look up typical columns, and so maybe they find one with a 2 micron particle size, and they notice that that's got a smaller diameter. And we talk a little bit about the effect of particle size on pressure and flow rate. And so maybe we come up with this set of conditions now, where we've got a shorter column, smaller particle size, lower flow rate. And so now we've got really good resolution and a runtime of now about 10 minutes. We can push this a little harder. The resolution we had before was optimized at about 1.4. And so now we got a runtime well under 10 minutes. And so now all the students can bring in a couple of samples. We can run replicas. We can run standards for the calibration curve. And so now we've designed an experiment that's really going to work for them in lab. Okay, so that's an overview of some of the things that you can do looking at an isocratic system, right? One of the things I really want students to learn about is the power of gradient dilution. And so to do that, what I'm going to do is I'm going to load another demo file. And this one is a much more complex system. And so this is a set of amino acids. And here we're starting off with an isocratic system where we're using all water, no organic phase. And what you see is we have really, really long retention times, and many of the components don't ever come off the column. Right, so the first peak doesn't come off until 9 minutes for the first peak, and then the last peaks, they're never going to come off. So clearly this isn't going to work. So based on what they've done before, we could increase the organic mobile phase, and say we go with 10%. And so now we get all the compounds are coming off the column, but the lysine not coming off for hours. And so clearly this is not going to work, right? And so we go and we bump it up some more, say 20%. And now we got the runtime down to an hour and a half, an hour and 40 minutes. We've got everything coming off the column. So this is not ideal, but at least it could work, right? Can we push that harder? Can we go up to 50%? Well, we've reduced the runtime significantly, but a couple of the components now, because there's such a high organic phase concentration, a couple of the components now never come off the column, right? And if we go up to 75%, it's even worse. So what you'll find here is there's really no options that work. And if we look at that resolution map, the software actually tells you that right up front, right? So it does not matter what the percent organic phase is. There is no sort of good solution. And even here, that's sort of the best solutions right there. There's a number of components where the runtime, it's just crazy, way too long. So this is when we can introduce the idea of a gradient. And so in an isocratic system, right, the mobile phase composition is constant. What would happen if we started off the experiment where there was no organic in the mobile phase, so that those initial components come off and are well resolved, and then we increase it? And so we could do an experiment where we started off with 0% organic, and over the course of an hour, we raised it to 100%. And what you see in the chromatogram, or if we look in the peak table, is now we've got an experiment that's going to work, or it's close to working. And so all the peaks, almost all the peaks are resolved. Everything comes out in 30 minutes. There's just one pair right here where the two peaks aren't resolved. All right. But this idea of a gradient, then you can ask the question, well, if that's what happened if we did the gradient over 30 minutes, 60 minutes, what would happen if we speed things up and we try to do the same gradient in 30 minutes? And you'll see we still have almost all the components now. 8 and 9 right here are overlapping now, and 6 and 7 are still overlapping. So we've lost a little bit. We've lost the resolution of one of the pairs, but we've dramatically increased reduced the runtime. And so the next step then that we can do, and typically during lab, that's about as far as we might ever get. With the software, though, it's also easy to do not just one-step gradients, but we can do a two-step gradient. So what if we go slowly at first to get all those initial components resolved, and then we speed up the gradient at the end to get everything to come off faster? And so here with this two-step gradient, now we've got an experiment that's running in about 30 minutes where every single thing in the peak table is resolved. The software, right, you might be able to come up with a two-step gradient like that just playing around. But the software will go even further, and it will let you simulate multi-step gradients. And so in the methods generator, you can actually set up the parameters that you want to optimize. So we want the resolution to be between 1.5 and 1. We want the runtime to be ideally less than 30 minutes, at worst less than 40 minutes. What are sort of suitable K-prime factors? And then you run, the program will run through and vary the gradient system to try and optimize it. And so it came up with this three-step gradient that was able to clearly resolve everything in under 30 minutes. And that was sort of the best, right? The suitability factor is calculated based on those parameters that you put in and the importance you give to them. It generated, this was the best option that it was able to find with a three-step gradient. And so that's what I did with my students. I walked them through this, and based on this, it seems like they were able to learn a lot about experimental optimization, the different parameters that are available for liquid chromatography, and how you might go about doing this experiment. So in summary, sort of the ACD software, it saved the day. It was a really efficient use of time. I was able to have really high quality discussions with my students. There were more parameters that we were able to adjust in the software than we would normally be able to do in real life. The trade-off is they didn't have the hands-on experience with the instrumentation, and they did miss that, and they acknowledge that. And then finally, I want to acknowledge and thank ACD Software for making this available to me so I could do this, and also special thanks to Michael for his help in making this happen, and his collaboration and patience with, I called him in a panic to try and figure out what to do. And so thank you very much. If anybody has any questions, I think we've got a few minutes left for question and answer.